that's a special case for infinite swept wing. To solve for the general cases, we need also to go through the integral boundary layer equation derivation for 3 dimensions. So because we already did this for 2 dimensions, I'm just going to remind you what is the 2-dimensional integral boundary layer equations and generalize to 3D. So this is 2D and 3D. So in 2D, we defined let me see. So we defined the defect to be the mass flow defect. I think we called m dot, right? To be the integral of rho ue minus u dy, integrating from 0 to the edge of the boundary layer, delta 99, let's say. Okay. Now in 3D, we not only have u and ue, we also have w and we. So the mass flow defect is no longer a scalar, it's a vector. So in the 3D case, what? Q. Yeah, so let's define, let me see, let's define this big M to be a 2-dimensional vector that is always tangential to the surface, right? Remember, we are doing a lot of 2-dimensional vectors. We can take divergence of the x and z directions, right? So this is another 2-dimensional vector that is a combination of x and z directions. So this is an integral of rho times, yes, use the q, right? QE minus q dy. So that's the mass defect. And in 2D, the mass defect helps us derive the equation that if I have the derivative, okay, so in this case we have a ODE, dm dot dx. We use the control volume to do this. We derive that has to be equal to rho times vi at the wall. And vi is what? Vi is the wall normal velocity of inviscid equivalent velocity, right? And the inviscid equivalent velocity is a velocity field that satisfies the inviscid governing equation everywhere, including inside the boundary layer, and also conforms with the viscous solution outside the boundary layer, right? So this is Vi. In the 3D case, we have the same thing, but we no longer have dm dot dx only. We have what? Think of this as derived from the mass conservation equation. We now have the divergence of this m in the x and z directions, right? So it's basically dmx dx plus dmz dz is equal to the same rho vi at the wall. All right. And as you can imagine, solving the equations on the wall is basically solving a 2-dimensional PDE just on the wall, as opposed to solving ODE on the wall. It's somewhere in between solving an ODE on the line versus solving a PDE in the 3-dimensional space. Okay. So in 2D, in addition to the mass to the mass defect, we also have the momentum defect. So this is the mass defect. We also have momentum defect. So the momentum defect is defined as an integral of ue minus u times u dy, right? And in 3D, we also define momentum effect, but we have 1u, 2u. So the momentum defect is now a what? It's not a scalar, it's a tensor now. It's a rank 2 tensor in 2D, which means if you represent it mathematically, it's a 2 by 2 matrix at every point on the surface. Okay, so let's define this P. I use the double vector sign to denote a rank 2 tensor is equal to integration of rho. I think I forget to have a rho here. Rho times QE minus Q. Here is not a dot product, it's just a cross product of Q dy, right? So this gives you one dimension, this gives you another dimension on this tensor. And how do we derive the momentum defect law? We use a combination of the mass conservation equation and momentum conservation equation, right? If you remember, we use the momentum conservation equation to derive an equation satisfied by this momentum defect, but the resulting right-hand side has a wall normal velocity in it, right? Then we used the mass conservation equation, actually use this equation to get rid of the velocity on the wall, to represent the right-hand side as a function of dm dot dx. So the resulting equation we got in the two-dimensional case is, so let's say this is P. We have this, again, it's an ODE, so dp dx. It turns out just to be our tau at the wall, right? Wait. I think tau on the wall, and we also have a different. We also have a term that comes from this v at the wall. I think we also have. No, we also have m dot times due dx, right? Yeah, I think we have a term like this that comes from the comes from this uv at the wall term that we have to deal with in the momentum defect equation, and that term actually helps us combining this term and this term into a equation that describes the change in the momentum thickness, right? d theta dx.
Is that the convective flux of Vi?
Convective flux of Vi.
So m dot is like sort of the mass entering.
M dot is this. M dot is the mass defect. Right. So the evolution of momentum defect has two sources. One is tau at the wall, right? That's if you have a lot of stress at the wall, that slows down the velocity and increases the momentum defect. And the second term is this. It's a contribution from the pressure gradient. If you have a favorable pressure gradient, that means you have a positive dU dx. That actually removes the momentum defect from your from the system.
So that m dot, wouldn't that be then a quantification of the flux coming through the, so from outside into the boundary?
No, this m dot is the mass defect. I mean, this is the two-dimensional derivation, right? This is the 2D stuff we did I think a few weeks earlier.
Oh, okay. I see.
Yeah, this m dot is just the mass defect, right? And if you and the units are right. I mean, this dU dx. We have a dx here. We have a dx here, and we have a p here. M dot here. The unit difference between p and m is actually u. So it's I think that's right. And the two-dimensional, the three-dimensional analog of this is that if you write down the divergence of p, the x component of p, So the x component of P itself is a vector, right? And that plus m, which is another vector, dot with the gradient of UE is equal to tau x at the wall. So this comes from the x momentum conservation equation. Okay, so this is the okay, so this dpdx is now becomes the divergence of px, and this term now becomes this, right? This term was originally m dot times dv dx, now becomes m, the mass defect as a vector, times the gradient of UE outside the boundary layer, and is equal to the x directional wall shear stress, right? That can be derived from the x momentum conservation equation, and the corresponding z direction momentum conservation equation is basically the same, except for here is not UE, is WE, and it's not tau x, it's tau z. So we get 1 equation, 2 equation, and 3 equations. And also here we have up to now 3, not 3, we have I think we already have, let's see, 1, 2 vectors, and we have already 6 variables here, right? 2 mass and 2 momentum defects.
Isn't that PZ in the last?
Yeah, it's PZ. Yeah, thanks. That's good. Okay. Finally, in order to have so if we do something equivalent to Thrice method, these 2 equations are enough. But in order to have the 2 equation method, we also have a kinetic energy defect. And we went through that really quickly, and the defect is defined as, K is being defined as integral of, in the 2D case is UE square minus U square times rho U dy. And in the 3-dimensional case, again, the kinetic energy is going to be a vector. So it's no longer going to be a tensor, because the square in the 3D case is now the norm, like the square of the norm, because that's in the kinetic energy. Is going to be integration of the absolute value of UE square minus the absolute value of U square.
Q.
Oh, Q, yeah. Thanks. Times rho Q dy. Okay, and the equations we're going to derive here, I'm just going to skip the 2-dimensional version. It's basically the divergence of K. That's again from the conservation law, from making a control volume, plus wait, I think this ends up to be just a 2 times the dissipation, where the dissipation is defined as the integral from 0 to delta tau x y times partial u partial y plus tau zy times partial w partial y dy. Right, so in the 2D case, we only have this term. In 3D case, we basically have the dissipation being contributed both from the u velocity and w velocity.